completely.
Yeah, so yeah, welcome everybody to another Shocklab seminar. We're very happy to have Callum here today, who is a junior researcher at InstaDeep, and is going to be telling us about the paper that was published. Where was this published? Remind me.
It was published at 2 workshops at New last year.
Awesome. Yeah, and generalizable
Yeah.
agents for neural network optimization. Over to you.
Cool. Thank you. Yeah, great to be here. Thank you, guys. So this is going to be a talk about GANNO. It's just going to be a brief chat. And this was a nice joint work. You can see a bunch of people there. And I'll dive in. So thanks so much for having us. Yeah, this was presented at 2 workshops last year at Europe's Optimization for Machine Learning, and also a workshop for advanced neural network training, and it seemed to receive some nice positive comments and some feedback. And the nature of it being a workshop is that it is kind of some cool initial ideas. We didn't get necessarily amazing results across the board, but we found some really interesting things which could kind of be built on. And it was a nice collaboration from InstaDeep, but then also some Professor at Wits, and then Co here as well, some Sarah from Co here, which was great. And yeah, so firstly, what is GANNO? This idea of generalizable agents for neural network optimization? It's quite a mouthful. So this is kind of a system figure overview of GANNO, and there's quite a lot happening. So I'll just kind of break it down at each point. You might kind of recognize the typical RL pattern here, but let's just dive into what's happening. So in this RL situation, the environment itself is a neural network supervised learning problem, right? So we have some sort of data set. Say we have fashion MNIST, for example. We have an optimizer, so HGD maybe, and we have a neural network, say a CNN, right? And that itself is the environment. You can think of what we typically see in environments is, there's all sorts of dynamics and stuff. And you can imagine how this happens in the supervised learning problem. If we probe this environment, there are all sorts of interesting things happening and all sorts of things that we can then observe as agents, right? And we can take observations both at a local level, and when I say local, I mean a layerwise level, right? And so at each layer of the network, we have all sorts of things like, say, the mean of the weights in that layer of the network. A global state might be the training accuracy that environment, that supervised learning problem is currently exhibiting, right? A training accuracy or test set accuracy, or some state of the optimizer, or some state of the network. And so if you look into the paper itself, I won't bore you with the details now, but there's a whole long list of our observations in terms of accuracy and loss, the initial learning rate, the weight decay, the layer depth, how deep we are in the network, the norm of the updates, the weights. You can kind of imagine all sorts of combination of observations. And then, of course, we also have a reward. And the reward is also coming from some sort of defined metric that we want to optimize. So in this case, it might be the training accuracy. So again, we have a data set, we have an optimizer and a network. And inside that environment is actually a supervised learning problem, right? And we observe various things about that environment, and we get a reward, much like a typical RL problem. Now we have agents, and we've framed this as a multi-agent problem where we observe layer-wise dynamics as well as a global state, and each agent essentially controls then a corresponding layer, and the actions that these agents take, right, could be a variety of things. You could imagine all sorts of hyperparameters that we typically control in a supervised learning problem. In our case, we control the learning rate to kind of keep it fairly simple. But you can imagine an agent that decides, I'm going to change the learning rate, I'm going to change the weight decay, I'm going to change various other things within the network. And you can kind of imagine that this lost landscape of the supervised learning problem, your agents are like driving this little car, and it's taking actions much like a little environment that is driving a car over a landscape, right? It's taking actions to speed it up or slow it down, or by changing the weight decay, we're actually changing the landscape itself, which is quite interesting. And so that's GANNO. That's kind of this high level idea of we are trying to control these agents that are acting in this environment through, in this case, adjusting the learning rate, observing the dynamics as that supervised learning problem is evolving and unfolding, and trying to learn what actions to take when we get particular observations. In this case, yeah.
Yeah,
Please.
can I ask a question there? So in terms of the local observations, you're sort of linking them up here with the network. You've got separately the optimizer there. Do you have, so would local observations include things like the steepness of the lost landscape in the area that you're around? Do you take that sort of thing into account?
Yeah, so I think we did look at the grads themselves, like the actual gradient updates, which would probably give, the closest indication of this steepness, but in terms of what we could, like the space of what we could observe is obviously quite large.
Sure.
I think what we ended up doing was focusing more on kind of network updates and network weights. And also when we're observing the weights, we weren't necessarily observing all the weight values themselves, but some sort of aggregate, like a mean of the weights. But of course, this framework is sufficiently general that you could hypothetically have something that looks at the whole network and has this like rich understanding of this large observation space. But you are correct in terms of you could also observe various things about the optimizer and the landscape itself.
Thanks.
Cool. So yeah, you'll see there we for GANNO itself, to control these agents, to learn agent policies, to adjust the learning rate, to take those actions in the network, we used independent PPO with shared parameters. And then also there's this idea of a depth embedding. So it's just some sort of indication to essentially enable agent specialization. Obviously, we're getting local observations, so there's a certain degree of that in that the observations themselves will be different at different layers. But on top of that, we also kind of, in the same way that we would typically put an agent ID, we have some sort of depth embedding. And that could be as simple as, am I the first layer? Am I a hidden layer? Am I the last layer? And you could, kind of imagine all sorts of interesting depth embeddings and kind of what kind of dynamics you would want to see at each layer and so on. I won't bore you with all the observations, actions, and all that kind of stuff, but you could read the paper for that. But this is the gist of what GANNO is. Before we go further, I kind of want to say, well, why GANNO? And the literature essentially isolates we isolated three kind of conclusions from the literature. One being that scheduling in the supervised learning problem is useful. And there are many papers that say, all sorts of handcrafted schedules, cyclical learning rates, these are very useful in supervised learning problems. So that's like the first conclusion that we found. Secondly, RL has been done in this kind of context for scheduling, for learning schedules. And it is effective, which is fantastic, and there's kind of proof of that in the literature. And finally, layerwise information is useful, and you can kind of see the thread that's forming here. Layerwise information being controlling layerwise learning rates has been shown to be quite useful. RL for controlling a global learning rate has been shown to be useful, and scheduling itself is useful. And we kind of tie this together with layerwise scheduling with MARL, where we kind of have this team of agents, each controlling a learning rate at each kind of level of this network, and hopefully cooperating in the typical MARL use case of cooperating to optimize some sort of global objective, which is, like improving the accuracy of this training. To kind of then sum up, the kind of findings that we found from this initial foray into these ideas, the strengths. Well, we first looked at a simple example where we train on a two-layered CNN looking at fashion MNIST. And now, again, there's this inner training loop of the supervised learning problem, which is this two-layer CNN, fashion MNIST, and I think it was Adam or SGD, I can't remember now. And that's now obviously a whole lot of training steps. And then there's this outer layer, which is the RL agents training on the observations and actions and rewards of that inside training loop. So in this case, we're looking at quite a simple version, and this is the reason it's simple is it's not generalizable. So like it's not generalizing, rather it's the things that GANNO is seeing during training is we're also evaluating on. And the first thing we see is that useful schedules are indeed generated. So here is episode 0. This is the initialization of our agents, and this is just looking at one of the agents' learning rates. So this is the learning rate at episode 0 of the first agent. And you can see it's just kind of bumbling around. Obviously, it's just exploring. It's kind of choosing fairly, just depending on the policy initialization. And you can see that the loss is not very good. Over time, it actually increases. And yeah, but what we see very interestingly is later on in this training, and our episode 40 refers to episode 40 in GANNO's training, right? The outer loop. We see this much better, much more controlled, much more interesting learning rate on the left, this episode 40, this blue here, we see it's a lot more controlled. It's almost cyclical. It's not necessarily periodic, but it almost has this periodicity baked in, where it's sending it up and decaying it. And the corresponding loss curve is that it actually goes down. And we can see an improvement in the loss curve, right? Which is super interesting. This is a useful schedule. And this generated schedule improves classification loss. And also it's reminiscent of some of the existing schedules. So if you look into the literature, exponential decay is a well-known supervised learning schedule, as well as SGDR. SGDR has this cyclical thing where it kind of sends up the learning rate and decays it and sends it up and so on. So that is a very interesting finding, right? Moreover, responsive schedules are generated. So we have the same problem, two-layer CNN, fashion MNIST. These are the two learning rates later in training, also, around episode 40. And we're kind of seeing some interesting things here where, the one agent is kind of doing all sorts of interesting things, and the other agent at layer 2 is also doing some interesting things. And what's fascinating is to look at the corresponding training accuracy when these agents are acting. And if I kind of just use my cursor here, you can see that firstly, the training accuracy is kind of plateaued. We've found this local optima, and boom, agent 2 spikes its learning rate. And sure enough, the training accuracy, you've almost escaped this little local optima, right? And then later on, a kind of more curious thing happens where layer 2 sends its learning rate up, and not immediately, if you I don't know if the resolution is sufficient here, but the training accuracy kind of goes down a little bit. But then the corresponding action a little bit later is that layer 1 then sends its learning rate up, and indeed it gets out of that local optima again. And so we're seeing that this responsive, it actually can respond to the dynamics of the network, which is the whole point of this RL approach, right? Is that we can observe what's happening in the network, and indeed then the agents can take the necessary actions. And if you think about it philosophically, this is kind of what we do when we babysit models, right? Is we are observing the network, we're looking at dynamics of the network, and we are changing hyperparameters. And the hope is that these RL agents, if we can give them sufficient information, and of course they can process this now high dimensional data, if we can give them enough flexibility to take actions and learn what to do, we are actually giving it the power to do what we do, but much better, and kind of respond to dynamics of the network.
Sorry, can I ask a quick question? Sorry, can you remind me, so what's the reward that the agents get?
So the reward that we went with was, I believe, the accuracy. We did kind of split. So we have this data set, which we split into like a train and validation set. And I believe it was the validation accuracy of the inside problem then becomes the reward for the outside problem, if I remember correctly.
And so that presumably is at the end of a single training run, it's the accuracy on the validation set.
Well, so you also, I think it was every 100 steps within the inside loop, we then process an outside loop. Sorry, I probably should have mentioned that earlier.
Sorry. Yeah. No, that makes sense.
So for a certain number of T steps, and that's also a hyperparameter, which we found, I think, was about 100. And yeah, so the inside loop trains for 100 steps, and then we kind of take an observation, take an action, and so on.
And so can I also ask,
yeah.
So here, it certainly looks like it's sort of got reasonable behavior, that the learning rate is going down, which you want, but then it's going down so far that the accuracy is plateauing, and so then it goes up again. How does this compare to just having a constant, moderately low learning rate? Like if you have a constant learning rate for each layer, what does the accuracy look like?
It's interesting. So I will actually mention in a couple slides this speaker of comparing, like essentially we talk about comparing it to things like constant and stuff, and there'll be some interesting dynamics that I will highlight there. One thing that Sasha just mentioned in the chat is that indeed I think we ended up doing difference rewards, which is this idea of what is the difference between taking an action versus not changing anything, and then you essentially compute two paths there and then compare them. So yeah. Very interesting that indeed responsive schedules can be generated, and we're seeing this almost layerwise coordination, or at least hints of it. We don't necessarily have definitive evidence, but we are showing we're seeing some hints of that, which is quite useful. The next strength is the signs of generalization and robustness. Now, I mentioned the layer depth embedding earlier because this was another kind of pipe dream for GANNO, is that ideally what we want is we want to be able to train on simpler settings where we can learn the dynamics of this neural network and hopefully then generalize to maybe a more complex network, a more complex data set, or a different data set, maybe even different networks. And you can imagine how each of those becomes more complex. You know, how similar is that loss landscape that it's traversing? And so we looked at training on a 2-layer CNN on fashion MNIST, and then evaluating on a more complex setting. So still a CNN, but a 5-layered CNN, right, with CFAR 10, which is a more complex data set. Now, a 5-layer CNN, because of this depth, embedding, along with sharing parameters, we can generalize to more depths, essentially arbitrary depths, which is quite useful. And here is kind of what I mentioned earlier. Now, I know there are a lot of numbers here, so I'll kind of just highlight some interesting things. Firstly, it's interesting that GANNO performs comparably. Now, the goal here is not to say GANNO outperforms everything, because quite frankly, these are handcrafted schedules that have been passed down through the generations. And many researchers have thought of these, like, you know, come up with these heuristics. And so the fact that GANNO can perform comparably with them is impressive, and we feel is sufficiently impressive. And more than that, it can handle a wide variety of initial conditions. So we say that it is both, it can generalize and it's also robust. And moreover, it's generalizing on a problem that it wasn't trained on. You know, we have actually increased the depth. We have actually increased the complexity. And so even though we do see HDDR you know, does quite well in some of these settings, GANNO does very well. And on average, across these initial learning rate conditions, kind of where we initialize the learning rate for the schedules and for GANNO, it does quite well. And so we see that it's competitive with handcrafted schedules, and it is also robust across the initial learning rates. Now, I'm going to speak to this point a bit later, but indeed, constant learning rates actually do quite well. And I think that this is going to be something we discuss later as a challenge of this paradigm, is that the difference between just doing nothing is actually not that big. And we are in supervised learning trying to squeeze out those little percentages. And that's very different to something like cartpole, right? In cartpole RL environment, your failure, your space of failure is kind of a lot bigger. If you just did nothing in cartpole, in like quite quickly you fall over. And so here, by doing nothing, you actually kind of get most of the way there. And we're trying to do this very fine grained control towards the end, which makes it quite a difficult problem. So then, yes, indeed, that was the science of generalization and robustness. Now, we also kind of then took it to the next step, and we tried an even more complex problem. So here's ResNet 9 layers, right, with residual network with fashion MNIST, now going to ResNet 18 with CFAR 10. And now we're also testing on another level. We're also going to look at different weight decay values. So not to control the weight decay, but initializing with a different weight decay to kind of see, can it generalize? This graph is quite a lot, so don't get too overwhelmed by it. But I just want to highlight some interesting points. So firstly, the random agent. So this is this blue line here, Adam with a random agent. It's a hard problem. It sucks. It struggles. When Adam tries to learn on this, it's just like, if I'm just a random agent bumbling along, it cannot solve this problem. And that's important because we are essentially showing GANNO is learning. It's not doing just something random, you know. Moreover, Velo is this learned optimizer, which we'll speak about a bit later. And now this is like one of the top optimizers out there, and this was, you know, quite a sophisticated thing. Even though it does really well with this purple line, right? It can learn with this purple line. With a slightly different initial weight decay value, it also struggles. It really struggles to learn, right? And we compare that to GANNO, which is a lot more robust. And so we can see the green and the orange curves here. Even though we don't come out, you know, the best across all optimizers, we're still a lot more robust to these different initial conditions. And that's the ultimate goal, once again, is that we can handle, because we are handling the dynamics dynamically, we are observing and kind of acting dynamically, we hope to be more robust. And then also, just to kind of reiterate, we trained on a 9-layer network, and we now evaluating on an 18-layer network, which is quite interesting because they're very different dynamics, you can imagine.
Sorry, can I ask another question there?
Of course.
So in terms of the training time for this, yeah, how does this compare? Again, sort of, you know, if you were to do a comparison, I've got a finite amount of time.
Yeah.
Yeah. What's the training time for this?
Yeah. It's a great question, and once again, something that we'll mention earlier, but I will kind of allude to it here, is that indeed you do have this choice to make where, you know, we could see earlier that a constant learning rate actually does pretty well. And, you know, also these heuristics exist. And so if they do pretty well, that's a defined thing. And so sure, it took a lot of like brain power to get to that heuristic, but at least it exists now. And so on the one end of the spectrum, we have these kinds of O of one learning rate schedules because they've been defined already, regardless of your problem. And then on the other end, you have these things like VLO, which are very sophisticated. But I think I mentioned it later, it's like 4,000 TPU months. So it's like huge. It probably killed, I don't know how many ice shelves to train this optimizer. And GANNO sits kind of in the middle. So a lot of our experiments, I think it ended up being about 6 hours on an A100, which is certainly not cheap, but it's orders of magnitude less than these learned optimizers. And the pitch is essentially that you train it in this simpler setting, and in the hope that it can generalize, which means that even though it's not as cheap as one of these predefined schedules, it still can generalize to much harder problems where we can imagine, the constant learning rate in a more sophisticated, complex, say you have a transformer now, it's going to be a very different story. It can't, that difference will become a lot bigger. And so it is regrettable that we couldn't kind of get to that level of saying, okay, well, hey, let's look at the transformer, training with the transformer where a constant learning rate will really suck and GANNO can hopefully do well. But that would be the vision that we're painting, right? Is that something that is sufficiently advanced, can process the dynamics sufficiently well, can then do it. I trust that answers the question, yeah. And I'll speak a bit more to it later. So yeah, that was signs of generalization and robustness. We also kind of want to highlight the fact that observing these layer dynamics is useful. I mentioned earlier that people have done RL for scheduling. And so what we wanted to do is kind of say, well, how about we ablate across various observations? And the ablations were as follows. We did this CNN example as before, earlier. But 3 ablations. Firstly, we only observed the current learning rate. So it's still a multi-agent problem. It's still layer-wise, all of that. But we only observe what the current learning rate is. And we kind of saying, are the other dynamics useful? Secondly, we only observe the training progress. And now the training progress being the only observation is essentially, you can imagine, in the flavor of a typical scheduling algorithm, because that's what a typical scheduling algorithm is doing, is it's a function of how far along we are in training, right? Often you think of an exponential decay, that function is defined by how long we been training, right? And then we also looked at a single agent, just one single agent controlling everything. And again, lots of numbers, but I'll highlight several things. So firstly, the learning rate only, it struggles both on average and with an appropriately defined initial learning rate, it performs comparably. But if you have a bad initial learning rate, by only observing that, it does really badly. And what we found is that actually all the agents were doing is if it only observed that, it would just send them to 0. It's like the safest thing for it to do is just send them right down to 0. And so you start at 0, your agent's going to do very badly, which is showing that it is useful to observe these dynamics. The time step only also performs actually pretty well. And with an initial learning rate, it performs quite well. And this shouldn't be too much of a surprise, given what we saw earlier, that with a well-defined schedule, a handcrafted heuristic schedule, if you have a good initial learning rate, it can do very, very well. But it's not necessarily as robust. And you see that at, again, a bad initial condition, it can't actually recover that performance, right? And so with an initial learning rate of 0, this thing kind of falls apart, and you see this high variance in the average. The single agent just doesn't do as well. And this is very encouraging for the MARL case. And here we see that GANNO does quite well across the board. Though there were strengths of GANNO, there were definitely challenges as well. And I'll highlight some of them here. So the one is that agent foresight is necessary for great performance. What does this mean? So what I haven't pointed to yet is essentially out of these handcrafted schedules, the rock stars, the ones that do really, really well. And they are these warm-up schedules, right? And there's talk of this in the literature, and you can kind of, you'll see that it's often recommended. And the idea of a warm-up schedule is that you start at 0, you start at some low value, you ramp upwards, and then you decay, right? And perhaps, you maybe do other things after that. But in this case, we looked at linear warm-up, so linear warm-up and then cosine decay, or the cosine one cycle schedule, which is defined by this paper. And indeed, you can see with a good peak learning rate, these things are really good. Like this was on this CNN problem earlier. These are the highest results in the paper, right? And indeed, when we try GANNO at a learning rate of 0, we just don't get that same performance. And the hope would be that we do, right? The hope would be that GANNO explores the space and finds that it can learn the warm-up schedule, right? Now, what's really interesting is if we kind of look at one of these peak learning rate, we look at an instance of the training of GANNO, this is what we see. So the blue is this cosine 1 cycle, which I mentioned here, and you can see it does really, really well when its peak learning rate is 0.01. So here, peak learning rate is 0.01. This is what the cosine 1 cycle does. This is like the elite learning rate schedule that we see in the paper. Now, GANNO, these are 3 instances of GANNO trying to train. And this is the learning rate that is yielded, right? Now, you can see that it's kind of learning the flavor of what it's trying to do. It's trying to send it up and then kind of decay it with all sorts of other interesting things. But you see that it doesn't have the confidence, if I can use the word so glibly, it doesn't have the confidence to send it right up, because what we saw in other parts of the paper is that a high learning rate, just sending it high, just making it a very high learning rate, does terribly. It's a bad idea. And you need to have the agent foresight, if we can call it that, to send it up, but then know later in training also to send it down. And so there's almost this, I wouldn't say sparsity of reward, because the reward itself, the reward signal is actually dense, right? We're getting the training accuracy all the time. But there's this sparseness, or there's this foresight that's necessary of knowing that, okay, yes, I need to send it up, but then I also need to send it down. So it has the steepness, it has the capability of, sending this right up, but it also needs to know that later on. And I think what ends up happening is that it's acting a little bit more conservatively. So it is sending it up, but not too much. And at other points in training, it probably tried, and it sends it up, but then it starts doing badly, and it says, well, this is a bad idea. So that's one of the challenges. Yeah.
Can I just ask another question there? So you spoke about the fact that there is generalization, but it also seems like a pretty hard thing, in the sense that it seems that one might overfit in terms of finding a training schedule that works well for one, and maybe it works relatively well for another. But they're different problems, they're different loss landscapes. Do you expect it to be able to generalize over tasks, as well as something which has been designed to be general?
Yes. Now, it's a great question. And I seem to remember there were some steps that we took to make sure that it wasn't overfitting to the inner training loop. I don't know if Sasha wants to come in with anything, but that is definitely a problem, right? Is that we don't want to overfit. In the same way, it's kind of like an RL. We speak less about overfitting in RL as in supervised learning, where it's kind of a lot more clearly defined. But I think I think what we could find is training for too long on one supervised learning problem. And I think maybe we just didn't get to that amount of training. You would eventually, it would memorize the dynamics of this environment perfectly.
Could one also look at sort of training over multiple different tasks?
Yes. So that's a great point. And that was the original goal, was, GANNO sees not just this 2-layered CNN, but also the ResNet 9, and also maybe some other interesting problem, and not just fashion MNIST. And we're seeing this kind of collection of data sets and networks, such that it can almost capture something interesting about neural network dynamics. And we didn't actually get to that point, but I think that would be the optimal way of doing things. Sasha, I don't know if you have anything to add.
Can I ask a quick question?
Oh, yes, of course.
Sure. I was just wondering, as far as what the agents see, when they're, deciding what to do next, do they just see the current validation accuracy, or I think you said it was like a difference reward, or are they seeing like a sequence? The current validation accuracy and also the past ones, like how does that representation work?
So I think in the eventual thing, we had that it's only seeing the current, I'm just looking at the appendix of the paper right now. It seems like I think we just observed the current test accuracy and training loss. I think the hope would be that if you had some sort of recurrent system on the outer loop, that it would have, some sort of sense of where are we going. But that is also a good point, and I think it might be mentioned a bit later, where and there were lots of discussions about this, at least, of like, yeah, you know, an agent doesn't just need to know what the current accuracy, it kind of needs to know that curvature of the training curve. And yeah, it's a great point. I don't know also if Sasha, if you want to speak to that point at all.
Sure, yeah, I don't really have much to say on that one. I think I actually can't remember if we used recurrent networks or not.
No, I don't think in the final solution. At times we did. We tried a lot of things, which is typical for Rhys. And there were a lot of kind of open problems that we felt like we hadn't, you know, didn't get to.
Yeah. So I think absolutely recurrent networks will help there. And for the generalization, yeah, I was going to mention exactly what you guys talked about, which was training on like different networks or different data sets, just generally different problems. I think what was a lot easier to do was we try to generalize to different initial conditions, which I think Callum's already covered. So different initial learning rates and different initial weight decays, which I think we did relatively well at generalizing for.
Yes. Yeah. Sorry, I forgot to highlight that that in training, the agents essentially sample uniformly over orders of magnitude for an initial like learning rate and weight decay, I think, as well. So it's controlling the learning rate, but the initial settings for those are kind of sampled across orders of magnitude, which did help with generalization. Yeah.
But in a sense, what you have, so if you're looking at fashion MNIST, you've got the loss landscape is fixed and you're moving around that loss landscape. And what you're learning, in a sense, is as you move around the loss landscape, how to alter the learning rates. But if you're not using the structure of the loss landscape itself as part of the observation, it doesn't know how to associate one with the other. And then you're taking that, you know, the learning rate scheduler into an entirely different landscape, which, you know, may not be completely different, but it's really a different landscape. And so it's not that surprising that if it doesn't have information about sort of local information about the gradients in the loss landscape, that it wouldn't necessarily generalize that well.
Yeah. I think that I mean the hope was, so I do see like we did process the norm of the gradients of each layer, but I suppose that you are correct that we still don't have like sufficiently fine-grained understanding of that loss landscape to then expect our agents to traverse it.
Yeah, in a sense, you'd want to have the full Hessian point.
Yeah, and I'll speak to this a bit later, but I think that kind of a retrospective on this whole project would be to actually first go to the trivial case of like, hey, suppose we had a, you know, one layer MLP trying to learn sine of x or something, or like trying to learn some sort of function, not sine of x, but some sort of polynomial, and then kind of build from there such that we can consider what does it mean if we actually consume the whole neural network, you know, before we start trying to like distill the network in, you know, like by looking at averages and whatnot. Yeah, very interesting. So yes, agent foresight is necessary for great performance. This is something that was discussed earlier, so I won't spend too much time on it, but understanding agent success, you know, a constant schedule in these simpler cases yields a very similar actually result to what GANNO can achieve, and you know, even the best learning accuracy in the paper for this problem we saw earlier was that warm-up, which was 77%. So the difference is still pretty tight, and you can imagine why that's quite difficult. Now there are some solutions, so things like reward shaping, so difference rewards is, you know, what we looked at. And we were also only later on thinking, maybe there's some interesting thing where you actually look at offline RL, where you, in that supervised learning process, you actually generating data, you're recording that data, and then you apply your RL thing. And then we're also looking at perhaps things like centralizing the critic and whatnot. But yeah, some interesting challenges there of what it means for the agent to actually, you know, be doing the right thing. Yeah. Then kind of a final point. So Velo, once again, is this learned optimizer, meta-learned optimizer, and it took 4,000 TPU months. I mentioned a bit later. And it does very well. It's expectedly, it does very, very well, and it is still hard to compete with them. But now what's interesting is, and I've kind of put this challenge there to indicate that it's like the flip side is that we also suffer from computational difficulties where we might not be on that order of magnitude, but it is still not the cheapest. It's not as cheap as necessarily just using an off-the-shelf handcrafted heuristic. And so, yeah, thousands of TPU months for Velo, GANNO 6 hours on a single A100, and we kind of have this, handcrafted schedules are definitely cheaper than GANNO, but GANNO is certainly orders of magnitude cheaper than Velo. And our justification there is saying, well, of course, Velo now works because it's this meta-learned optimizer itself rather than a schedule, but subsequent developments of Velo, say you have a new problem, a new architecture, do you do those thousands of TPU months again? How generalizable is it? And so the hope, I think that hopefully GANNO can point us in this direction of, if we can get it right, you have this thing that is sufficiently generalizable. Sure, there is a computational requirement that's sitting kind of in the middle here, but it allows us to process new data sets, new challenges, new network architectures, hopefully with a fairly rich understanding of neural network dynamics themselves, rather than just throwing compute at it. That was GANNO. I think, once again, to just reiterate, I think in hindsight, they were probably, the lesson was to go on a much simpler level and start at the bottom and say, can we learn a very simple function with a very simple neural network, and then build from there and start to see the interesting dynamics before we just throw it at a bigger problem. And I'm not saying we didn't do that, but I think we could have been a little bit more kind of thorough with that. But nonetheless, we're very happy with the interesting observations, and we kind of wanted to put it out there to say, look, this is definitely, there's something here. There are lots of nuggets here, and we hope that this research can continue, because the end vision, the pipe dream is something that is quite wonderful, which is you don't have to babysit your model. You get your agent to, or your agents to babysit your model. Yeah. So if there are any questions, happy to try field them.
Awesome. Thank you so much. Really, really interesting. Any questions from anybody?
I'd just like to ask, did you consider other